Um, Hello everyone. Today is Saturday, June 13th, 2026, and I'm your host, San Nohani, bringing another super fun and exciting radio broadcast. I hope you're all having a fantastic weekend so far, and that you are ready to dive into some really cool science with me today. That is right. Today, I'm introducing a trending article from the archive, and it is a really fascinating one. The title is Lab VLA, Grounding Vision Language Action Models in Scientific Laboratories. The URL is https://arcsarf.org/abs/260 6.13578vwin. It is long, but do not worry. I am here to break it all down for you. It's easy to understand and super interesting. So, let us start with the big problem that this paper is trying to solve. In my mouth, I can read thousands of research papers, can generate new hypotheses, and I can plan out the exact steps for an experiment. But when it comes to the actual physical act of doing the science, like picking up a beaker, pouring a liquid, or pressing a button on a machine, the eye is totally stuck. The physical phase of an experiment still falls almost entirely to a human operator at the bench. The gap between digital reasoning and real physical work is huge. And it is not because the eye does not know what to do, but because it does not have the right body or the right training to do it. Now you might be thinking, and do we not already have robots that can do things? Yes, we have vision language action models, or VLA models for short, which help robots understand what they see and hear and then take action. But here is the catch. Existing robot policies are mostly trained on household chores and tabletop demonstrations. They know how to pick up an apple or open a kitchen drawer, but they rarely encounter the delicate instruments, transparent liquids, or strict protocol workflows found in chemistry or biology labs. Lab manipulation is way harder than everyday tasks. Using a pipette for transferring a chemical requires fine spatial precision, and a tiny mistake could ruin an entire experiment. To solve this, the researchers created something amazing called Lab VLA, and a data engine called Robo Genesis. Since collecting data in a real lab is incredibly expensive and dangerous, they decided to train the robots in high-fidelity simulation first. Robo Genesis is a simulation-based workflow and data engine. It rebuilds 3D laboratory environments from scratch. It uses text-to-image generation to create lab tools, places them safely on virtual tables, and then teaches virtual robots how to do atomic skills like picking, pouring, and stirring. It even adds domain randomization, which means it changes the lighting, the camera angles, and the background clutter. So the robot learns to focus on the actual task, no matter what the lab looks like. Compared to other technologies out there, like RoboCasa or Money Skill 3, Robo Genesis is way more advanced for this specific job. Other simulators just use. Fixed scenes are basic household items, but Robo Genesis lets you program long-horizon laboratory workflows across 16 different robot platforms. The model side, Lab VLA uses a two-stage training recipe. First, it uses something called FST action tokens to teach the language model about actions. And then it uses flow matching to predict smooth, continuous robot movements. They even use a cool trick called knowledge insulation, which stops the robot from forgetting its language skills while it is learning how to move physically. So, how does this apply to our everyday lives? Well, think about how long it takes to develop a new medicine or a new material. It takes years and years, partly because human scientists have to manually mix chemicals and run tests all day long. If we can have our robots doing the physical lab work, we can speed up scientific discovery exponentially. That means faster cures for diseases, better batteries for our phones and electric cars, and cheaper materials for everyday products. Let me give you 3 specific application examples based on the content of this paper. to show you exactly how this technology could impact the real world. First, imagine automated diagnostic testing in hospitals and clinics. There is a massive outbreak of a virus. Hospitals get overwhelmed with patient samples that need to be tested. With Lab VLA technology, we could deploy robots that safely and accurately handle thousands of blood or saliva samples. The robots would know exactly how to unknot the vials, use the pipettes to transfer the liquids into testing machines, and push the right buttons to start the analysis. This would take the burden off of human lab technicians, prevent exhaustion, deliver test results to patients much faster, which could literally save lives during a medical crisis. Second, we could have 24/7 autonomous chemistry laboratories for drug discovery. Right now, scientists have to go home to sleep, which means the experiments stop or move very slowly overnight. With an AI scientist paired with a Lab VLA robot never gets tired. The AI could plan a new chemical compound to treat a disease, and the robot could immediately start mixing the reagents, putting them on heating plates, stirring the mixtures, and observing the color changes. If an experiment fails at 2 in the morning, the AI analyzes the result, adjusts the formula, and the robot starts the next test right away. This continuous, non-stop loop could reduce the time it takes to discover a life, saving drug from 10 years down to maybe just a few months. Third, this technology is perfect for hazardous material handling. There are many experiments in science that involve highly toxic chemicals, radioactive materials, or dangerous biohazards. Human scientists have to wear heavy, uncomfortable protective suits, and they are still at risk if something goes wrong. By applying the concepts from this paper, we can send robots into these dangerous environments instead. Because Lab VLA is trained across different robot embodiments, we could use mobile manipulators that drive into a radioactive room, carefully transport open blast doors, and execute complex protocols while the human scientist sits safely in a control room far away. The results from their test were super impressive too. When they evaluated Lab VLA on a benchmark called Lab Utopia that achieved the highest average success rate among all the baseline models, it scored an average of 71.1% success on in-distribution tasks, and it barely dropped at all when faced with new, out-of-distribution challenges, scoring 70%. It was especially good at picking up labware, opening doors and pressing buttons. Pouring liquids is still a bit tricky for the robots, because tracking the surface of a clear liquid is super hard, but they are getting closer every day. They even tested this on a real, physical robot arm, and the robot was able to shake liquids, pour chemicals, and operate a magnetic stirrer with over 80% success. Just goes to show that training in a high-quality simulation can actually teach a real robot how to behave in the real world. The researchers talk about 4 levels of embodied laboratory competence, from apprentice to scientist. Right now, Lab VLA is at the technician level. It can follow a written multi-step protocol and do the physical actions. But it does not quite have the scientific judgment to change the experiment on its own yet. But Lab just having a reliable robotic technician is a massive leap forward for science. I think it is just so amazing to think about the future. A world where humans and robots work side by side in the lab, where AI does the heavy lifting and the tedious mixing, while humans focus on the big ideas and the creative problem solving. That is right. The future of science is looking brighter and faster than ever. Thank you so much for tuning in today, everyone. I really hope you enjoyed learning about Lab VLA and the awesome potential of robotic scientists. Have a wonderful rest of your Saturday. Stay curious and keep smiling. This is Sun No Penny signing off.